Hi guys, I hope everybody had a great vacation. If you are wondering what you can see on my desk, those are domino pieces. And we are going to use those domino pieces to present what mathematical induction is about. Well, mathematical induction is my favorite thing in mathematics. Well, I know I say it often, but I guess you can have more than one favorite thing. So I am going with mathematical induction as of today. So domino pieces. Why? Because if you think about this for a second, they will represent natural numbers. Natural numbers 1, 2, 3, 4, 5, 6, 7, and so on. Well, I have a whole box of them, but I only put that many pieces. I could keep going. And you know the domino effect? If I push this guy, the next one will fall, and then the next one will fall, and so on, right? So we are going to see how that relates to mathematical induction in a second. And mathematical induction, this is going to be a method of proving that some statements are true. So in mathematics, it's very easy to disprove something, because if you can come up with one example that is a counterexample, so if you can come up with something to show that the statement is not true, then you just disprove it. But in order to prove something in mathematics, you need to show that the statement is true always. So let's imagine some series of numbers, and let's try to show that whatever we want to say is true. So now you would have to test every single possible number. And of course, we are not going to be doing that. So, and again, I will show you examples in a second. So what we need to do is we need to use a method that is going to help us to make our life easier, of course. So induction, proofs by inductions will work for natural numbers. And let's see how this works. So if you look at my domino pieces, I know that if I push this guy, the next one will fall. So I know that it works for my n is equal to 1. Now, if I look at this one is my piece number 1, 2, 3, 4. How do I know that the piece number 4 is going to fall? I know that piece number 4 is going to fall because this one is going to fall. So what I'm going to do is I'm going to name it as my element k. Okay, and why k? For whatever reason in mathematical induction we use letter k. So I know that this one will fall. So if I can show that the next one false, then this is always going to work. So now if I know that this is k and I know I work with the natural numbers, this is going to be k plus 1. Now why is this important? This is important because I chose this as number 4, but I could have chosen this as any of my domino pieces. All right, let's see. Well, it worked. So in a second we'll do the notes. Keep remembering this. I know that at this moment it doesn't make too much sense for you, but we are going to put it together. And my suggestion is when we finish the notes, go back to this video and watch it one more time, just this beginning, and then we'll see if it makes a little bit more sense for you. All right, so I will take those away, maybe. And I have your notes. You should have those from before the break, but I will post them as well. I will post this copy, my copy, and I will post a blank copy for you as well. So make sure you fill it out. We are not going to do everything today. We will divide this lesson into 2. So what we are going to do is we are going to use mathematical induction to prove summation formulas and properties of divisibilities involving a positive integer n. We are not going to do the second part today. There are going to be 3 steps to prove the statement that the statement is true for all natural numbers. Our step 1 is going to be called a base case. Our step 2 is going to be called induction hypothesis. And this is where we are going to use the letter K. And then we are going to show that the statement is true for the next natural number k plus 1. So this is what we were doing a second ago with our domino pieces. You will notice in a second. The principle of mathematical induction, let Pn be a statement about a positive integer n. Then Pn is true for all positive integers n if and only if P1 is true. So you will see this in a second, how we'll take the first term, we'll show that it works. For every positive integer k, if pk is true, then the next term is true as well. All right, so let's take a look at the example. I already solved this, but I am going to explain this and run you by it. So what we have is, we have a statement. And this statement is that 2 plus 4 plus 6 plus, and this pattern is going to continue, 2 times n is always equal to n squared plus n. And this is what I said. If we didn't have the induction method, we would have to say, well, but how do I know it is true? How do I check that this is true? Somebody can say, well, this is given and it says it's true. Yes, but you always need to question yourself why. So let's take a look at this one. First, and again, you will see the structure is always going to be the same. We are going to set the base case. Base case is we are checking if our first term, so if n is equal to 1, if that is a true statement. So look at this one, n is equal to 1, I said this right here. So if n is equal to 1, the first term is 2. Well, this is a common practice. You will put the question mark, and on the right hand side, in place of n, you are going to plug in 1. So 1 squared plus 1, 2 is equal to 2. Your base case is true. So this is a good thing. Now we can move on forward. So my induction hypothesis is going to be, and again you will see that the structure for those proofs is always the same. We are going to assume that the formula holds when n is equal to k. So this is where I said, well, I want to see what is going to happen for my kth domino piece at the beginning. So the only thing that I am doing is, in place of my formula, everywhere in place of n, I am going to plug in k. So take a look, 2 plus 4 plus 6 plus, this pattern continues, plus 2k is equivalent to k squared plus k. So again, the only thing I did is I replaced the n with k. Okay, now, since you do that, or once you do that, you want to show that the formula holds for the next term, and if you use the k, then the next term is going to be k plus 1. So you want to show that this formula is going to hold also for the next term. So I want you to see what I did. I copied the formula the way I had it right in here, but what I am doing is I am adding the next term. And my next term, if the 2k is the last one, then the next one is going to be 2, but I have to add 1 to k. So take a look. It's like the when you work with the function notation and you plug in f of k plus 1, then everywhere in place of k, you plug in k plus 1. So now my right hand side, so notice I like my notation. This is the left hand side. This is the right hand side. I am going to have that my right hand side, notice I had k squared plus k. So now I am going to have k plus 1 squared plus, and instead of k, I said k plus 1. All right, so see what I'm doing is I am replacing, so on this side I am adding the next term. On the right hand side I am replacing k with k plus 1. All right, let's see what happens after. And this is a very important step. This part, and I underline this in here, I underline it in here, we know from this equation that it is equivalent to k squared plus k, right? So this is equivalent to k squared plus k, and what I am doing is, instead of this sum notation, the infinite long expression, I am just going to say that this is equivalent to k squared plus k, and then what I am adding to it is I am adding to it that next term. Okay, this is my left side of the equation. What you will always have to do is you will always have to clean it up. So notice what I did is I used the distributive property. So k squared plus k plus 2k plus 2, and then I combine those two like terms, and this is my answer. And then on this side I worked with my right hand side of the equation. So what I do have is, well, I need to square this. Remember, this is like multiplying by k plus 1, so it's a square of the first one, plus 2 times the first one times the second one, plus square of the second one, and then I still add k plus 1. Notice once you clean it up, k squared plus 3k plus 2, and this is exactly what my left hand side was equal to. Left is equal to right. So you want to write this after every single proof by induction, by mathematical induction, is conclusion. By principle of mathematical induction, the statement is true for all positive integers n. Now, I had a professor at Westfield State that was my favorite professor, and she would not give credit if you didn't write the conclusion. So again, one more time, what we are doing is we are proving that if a statement works for kth element, and kth element can be any number, and then if you can show that it works for the element after it, so k plus 1, then this statement is always going to be true. I know you already like it. So let's look at the next example. And the next example is, here is the statement. And we want to show that this statement is true for all positive integers n. So again, like we did in the previous example, we want to look at the base case, and the base case is for n is equal to 1. So my left hand side, the first element is 1, so that's my left side. And the right side, if I plug in 1 for n, I am going to get 1 squared. 1 is equal to 1. This is a true statement. All right, now the same way as we did in the first example, the second step is to have the inductive hypothesis, and I am going to assume that the formula holds for n is equal to k. Always the same thing. You are going to take your n, or whatever letter is used in your equation, and you are going to replace it with k. The next step is going to be that we now want to show that the formula holds for k plus 1. K plus 1, please remember, this is the next element. All right, and what we want to do now, this is the tricky part, we need to write it out. So you always start the same way as the given was, and then you are adding the next term. So in place of k, we are going to put k plus 1. So I want you to see I have 2, in parentheses I put k plus 1, and then I minus 1. And then I do exactly the same thing on the right hand side. Instead of k, I am putting k plus 1, and I am squaring that. Again, I have the left and the right hand side of the equation. And let's see. we will now work with the left-hand side. And again, this is very important part. We want to replace this mess with what we already know this is equivalent to. And this, from this equation, is equivalent to k squared. So this whole mess can be replaced with k squared. So now k squared plus 2, and then I didn't clean it up yet, so I have k squared plus this. I use the distributive property, so 2k plus 2 minus 1, and then k squared plus 2k plus 1. This is what the left-hand side simplified to. And then the right-hand side, if we look at this one, we have, well, this is just squaring this expression, so k squared plus 2k plus 1. Notice left-hand side is equal to the right-hand side. And conclusion, by principle of mathematical induction, the statement is true for all positive integers. And because we proved that if it works for the k, it is going to work for the next element. So by mathematical induction, we proved that our statement is true. As an assignment for tomorrow, I am going to give you a couple proofs to do, and then tomorrow we'll move on to something else.